All right. So physicist friends, yesterday at the end of class, we were talking about Hooke's law. Yesterday at the end of class, we finished by defining spring potential energy. So now in your toolbox of work and energy things, not only do you have kinetic energy and gravitational potential, but you've also got spring potential energy. This problem right here employs all three of them, okay? It is a conservation of energy problem with a ball that's being dropped from some height, y1, okay? It's got a mass of 2.6 kilograms starting from rest, falls a distance before striking a vertical coiled spring. Would it look exactly like this if it was happening in real life? No. But you get the idea. Like, imagine there's a platform here. It's just going to balance, right? This is a nice theoretical situation. And then that ball is going to stick to the spring, and the spring is going to compress as a result. Okay? So here's the situation, is that then it's going to go down a little ways. And my question that I'm asking of you is to determine the spring constant. What letter do we use for spring constant? Do you remember? K. It's little k. Not big K, because that's kinetic energy, right? But little k is the spring constant. I would like for you to try and set this problem up, okay? And I don't want you to just grasp at straws and try and set it up as a conservation of energy problem. Think about the fact that you've got a closed system here, right? The system includes what objects? I'm just going to talk you through this part. I heard somebody say to me, what? Elena, what'd you say? You said something. What objects are in the system? Just tell me one of them. I heard the spring and the ball. Is there anything else that needs to be in this system? You get to pick, but I would pick the, what'd you say? I love that your eyes were like, the earth, yeah. Because if you have the earth, then you've got gravitational potential energy and you can conserve that energy, right? If you don't include the earth, then we've got work being done. Let's conserve the energy. The ball, the spring, the earth. Those are the three things you need involved with the situation, okay? Energy at the beginning has to equal energy at the end because it's a closed system, okay? I'm going to give you just a few minutes to talk to your table mates, to write something down, move towards answering this question. Sound good? Okay, we'll regroup in just a moment. Hold on just a second. What should I just do? All right, let's go ahead and kind of regroup. Set this up and figure out what we need to do to answer it, shall we? So you all have spent some time doing this. I haven't been working on this problem, so you need to walk me through to get me where you are, okay? So all I know is that we had this ball that was up high, and then it fell, and then it squished a spring, and I want to know what K is. Where am I going to start? Get us started, Ira. What you got? We know the gravitational potential energy. Where?
So you know the height of the ball is above the spring.
Okay.
So you can use that for your height value and you know the mass.
Okay, so you're talking about the gravitational potential energy at A?
Yeah.
Okay, I just want to make sure that we're talking about the same place. Is that okay? So you're saying that I can find the gravitational potential energy at A because I know the mass and I know G, and I know the height because the height is 55 centimeters. Is everybody okay with that? Okay. So you can tell me that the gravitational potential energy at A is, so it's 2.6 kilograms times 9.8 meters per second squared times 55 centimeters. That's in centimeters, right? You guys notice that was in centimeters? So we need to convert that to meters, just making sure everybody's followed that. So what did you get for a value for that? 14.3 joules, says Ira. Can you guys corroborate that? Chris says he agrees with that. Emma, do you agree with that number? You're like, I don't know. Do I? Sure? Yeah? Eden, what about you? Yeah. Okay. So we now know the gravitational potential energy at A. That's cool. What are we going to do with that? Or what are we going to do next or in addition? Y'all had some really good conversation a moment ago. And there are a lot of things. There are a lot of good answers. I I want to make it very clear, friends, that on a problem like this, there's not one right answer. Lots of things to do. Yeah?
So 1/2 km squared is going to be equal to that gravitational.
Okay, say that again.
1/2 km squared is going to be equal to that.
1/2
Or ky. Yeah.
ky squared equals what?
The gravitation. 40.
Why?
Because once the spring's been fully compressed, then all the potential energy has been converted into spring.
Do you guys agree with that? I'm not saying that's wrong. I'm just asking. Because you just did there was like a whole bunch of physics that you squeezed into that little statement. What'd you say?
I just said he skipped some steps.
Skip some steps, but his physics is sound? Okay. So I want to back up for just a second. I want to know where this comes from, this 1/2 ky squared thing comes from. Because Chris, you're claiming that it's equal to 14.3, but that's a lot of physics happened between here and here. What is this? Okay, so this is spring potential energy. Spring potential energy where? At C. Do you guys agree with that? 1/2 kx squared is how to find spring potential energy. And you're telling me that we're starting here and we're going down to y. And y, okay, so it's going down to y. And so that's the spring potential energy. So that's how much energy is stored in the spring due to the ball pushing down on the spring. Okay? Now, and y is the 15. So we'll get there and we'll put all that in a minute. I just want to make sure. Oh, that's actually capital Y. I'm going to make that just so that I don't get confused later. Capital Y. All right. So you're claiming that these two things are equal. Where is that claim coming from?
So it starts at A, it's only potential energy, gravitational potential energy. Then at M, once it's fully compressed, all that energy will have converted into the potential energy of the spring for when it's going to recoil up.
Okay. So I need to do two things here. I want to make sure that I understand. The 55 is right here, right? Does everybody agree with that? I just want to make sure that I'm reading it right. 55 centimeters? Okay. And so I think really, Chris, if I'm understanding what you're saying, you're basically invoking conservation of energy. Is that right? So I'm going to walk us back because this is one of those things, friends, I've been doing this for a lot of years that I know is very, very tempting for physics students to do. And that's to say, oh, well, this has got to be this because this and this. And I will tell you that I sat for so many hours grading so many AP exams where they said, if it's a conservation of energy statement, if you don't have a statement of conservation of energy, you don't get the points. I don't want that to be you. Do you know what I'm saying? Right? I don't want that to be. I want you to be one of those kids that's got it, that knows it. So I'm going to tell you what you have to write down first. And the thing that you have to write down first is that the energy total at the beginning at A has to equal the energy total at C. Okay? Now, I will be completely honest. You don't have to have this line, but you have to have the line that comes next. That's the one that actually matters. Okay? If you don't have it, they can't give you points. So we need to look and see what flavors of energy we know of. What kinds of energy do we know about? Can you list them for me? What do we know? Gravitational potential, kinetic, spring potential. And there's a spring involved, and there's an earth involved, and there's movement involved, so all three of them are there. So we're going to go ahead and write them all down. So we're going to say gravitational spring potential and gravitational potential, apologize, and spring potential and kinetic at the beginning, this is all at A, has to be equal to, we're doing it in orange, gravitational potential plus kinetic plus spring potential at C. Okay? And there could be another part of the problem. We've done it before to figure out how fast that ball is going when it gets to B, right? And in that problem, then kinetic would be the thing that would matter. But at the very beginning, what is the velocity of that ball? And at the very end, what is the velocity of that ball? So is there kinetic energy in either of those cases? There is not. And so we're then going to get rid of it. But friends, you need to make sure that when you take a test on Friday, when you take a test at the end of the trimester, when you take a test at the end of that trimester, and when you take a test on May, whatever it is, you have to have this line. Okay? And I'm not saying that because I have, stock in a graphite company and I want you to use your pencils more. It's because I know that if you don't, you won't get the points for it. Okay? So I'm looking out for you. Okay, so then we know that these two are zero, the kinetics are zero. Is the spring squished at all or stretched at all in A? No. So there's no X, right? There's no displacement. So that means that one also goes away to zero, right? So I think it's accurate to say that the energy, the total energy at the beginning is exactly what we had said before, is that 14.3. Right? So I'm going to go ahead and just write down that U sub G at A, which, oh, by the way, we calculated was 14.3 joules. That has to be equal to the total energy at the bottom. Is there spring potential energy at the bottom? There is, because the spring has been squished, right? So for sure there is. We know that's true. So I'm going to write that U sub S at C, and we know that that's the 1/2 ky squared. Is there any gravitational potential energy at the bottom? You're changing your story, are you? Why? Why did you change your story?
Because our reference point is at y equals 0, and so that's where h is above. So now we're below that by a factor by 15 centimeters.
Yeah. So in the picture, they decided that h equals 0 here. So they have positive gravitational potential here, 0 gravitational potential here. Tell me about the gravitational potential at C. It is negative. What? It just means that it's below wherever you decide y equals 0 or h equals 0. Would it be okay to put my h equals 0 line down here? Yeah. But what would I have to do?
You have to adjust h.
Yeah. This thing, my h would have to be whatever that is. That's going to be what, 70? Yeah. Yeah. So indeed, there actually is gravitational potential at C. We need to acknowledge it and we need to, take it into account. Oops, that should be a C. Excuse me. Okay. If you haven't yet done the math, go ahead and do the math. I'm going to write out a couple more things and figure out what K is equal to, okay? Go ahead and do that real quick. We're going to just kind of cruise on through here. So that's equal to 1/2 K. That's our 15 centimeters, so 0.15 meters squared plus, that's mgh, where h is negative 0.15 meters. 14.3 joules. Again, reminding ourselves that we're solving for K. That's what we're looking for. If you haven't gotten it, plug it in. If you have got it, check with your table. Not the table itself, but the people that are sitting around the table talking about physics with you. Yeah, that's the 0.15. What did you say? The mass was given. It's 2.6. Yep. Sorry, it kind of was hiding over there, wasn't it?
Oh no, I was just going to use, if I was going to use this one.
Oh, got you. Yeah. How's it going, team? Is it very large or very small? Okay. That's okay. Part of the reason we're doing this is to get a sense of what a K could be, right? What a K could be. So, Eden, would you be willing to share your very large K value with us? I mean, sure. Yeah, you are welcome to. Chris believes in you. Chris, did you also get a very large number?
I think it's the perfect size, actually.
Oh, okay. Oh, okay. What did you get?
1,610.7.
1,610.7? Do you guys agree? Yeah? What are the units of this? There are units.
Oh, yeah.
There are units. Remember when we did Hooke's law to start? We had force and distance, and we said that K was our slope. So if you remember that, you can remember what the units are. The slope of a force versus distance graph. Newtons divided by meters, right? Newtons per meter. So what does this mean? So let's just because we haven't really processed a question like this before. We've never actually calculated K before. What does this mean? It means that it takes 1,600 newtons, 1,600 newtons of force to compress a spring a meter. Does that make sense? Okay? To compress a spring this far. That's and it gets harder and harder the further you push it, right? You have to take more and more force the further it goes. So even though this seems like a really huge number, it's not outside the realm of possibility for a number. Okay? So I don't want you to stress about oh my gosh, it's enormous. Yeah, little numbers are a little sketchy to me when you're talking about this stuff. How are we doing, team? Are we okay? Issues or questions on this one? I'm gonna throw one more kind of energy at you right now if you're ready. All right, let's do it. Last kind of energy for unit 4. There are more energies, but for today and for this unit, we're only gonna do one more. I'm gonna remind you, friendly reminder of the Work-Energy Theorem. Do you guys remember what the Work-Energy Theorem says? Help me out. Work equals delta E. It's pretty simple, right? Work energy. Work-Energy Theorem. Yay! Work equals change in energy. Anytime you do work, you change the amount of energy the system has, right? Okay? And we remember that work is also equal to force times distance, right? So if you apply a force over a distance, then you change the amount of energy in this open system. How are we doing so far? This is not a surprise, right? Okay. There is a force that we've talked about in other parts of our year, but we haven't really talked about lately. We haven't acknowledged, and some of you have gotten really mad that we haven't acknowledged in some formal ways, right? And that force is a force of friction. I want you to think about, if I have an object, some kid left their Altoids box, so I'm totally going to just use it right now, right? If I apply, so I want you to think this in terms of conservation of energy system. Are you ready? So I'm going to apply a force. So, okay, let me back up. Back up, Carbling. Don't get over it. Don't get too excited. Tell me what kinds of energy this has right now. Does it have gravitational potential if I call H equals 0 at the table? Does it have kinetic? No. Does it have spring potential? There are no, this is not a trick Altoids box. This is just an Altoids box. So here's the thing. I'm going to apply a force over a distance. And by applying a force over a distance, I am going to give this system of the box some energy, yeah? What kind of energy if I just kind of push it this way? What kind of energy am I giving it? Kinetic. Everybody good? Okay. But, so if I do that, as long as I'm applying a force over a distance, it's going to add energy to the system, right? And then after I stop applying energy, or stop applying a force, no more energy, which means that energy should be conserved and everything should just keep going on forever. That seems to make sense. So let's watch. Are you ready? Here it comes. This is I've never done this before, so this is brand new thing right here. Can you see Emma from where you are? You might need to get up because it might blow your mind. She's like, I don't want to get up. Shh. Come on, Caroline. Okay. You can see it now? Okay, here we go. Here, ready? So no energy. I'm going to apply a force over a distance. It's going to give us some energy. It's going to have energy forever. Here goes. Have energy forever?
Energy forever.
It doesn't have energy forever. Why? I applied a force over a distance for here. And I gave it what kind of energy? Kinetic. And then it's got kinetic energy. It's a closed system, so everything's just going to keep going forever. But clearly that's not what happened. Were there any other forces acting on this box of Altoids?
Yeah.
What for? There. I get a high five for that. He says, well, there must have been. Right? There clearly was, because the amount of energy changed, because how much energy is there now? None again. So there must have been some force applied over some distance to change the amount of energy from some to none. What was that force? It was friction. The force of friction can apply a force over a distance, and it changes the amount of energy, right? Or can I make it into a new kind of energy? Where does that energy go? What does friction generate, friends? It is thermal energy. Yeah, answer.
Do we just ignore the cosine of theta part?
I mean, no, but I just am lazy. So I guess yes, but no. The cosine of theta. So when I was applying a force at 0 degrees. So then it was 1. And friction, well, that's a good point. So friction was applying a force. Let's draw the picture, shall we? Because that'll make it better. Here we go. Here's our Altoids container. Here's the table. At the beginning, it was going, and it was going to travel a distance this way. And which way was the force going, friends? What's that? The opposite way, right? It was going the opposite way. So we had a force of friction going this way. Force of the surface on the box, right? FF. So the cosine of theta, when theta is 180, so that would be, what is it? Cosine of 180? Anybody? -1? -1? Yeah, right? So if it's -1, that means that we've got negative energy, right? We're losing energy from the system. Yeah? Or we can say that that energy that was kinetic, okay, because it was kinetic now, turns into this thermal energy, right? Right, that goes off into the system as a whole, okay? So you can either say that friction, again, it's that whole thing. It depends on if you're talking about it's a closed system or an open system. If you're not talking about the system as a whole as a closed system, then that friction just takes away energy. Or if you want to close up the system, then you have to include the room as part of the system as well. Because if I take this thing and I do this over and over and over and over, and then I feel the bottom of this box, what's it going to have done? It's going to get warm. It is. It actually warms up, okay? Which means that energy is being dissipated into the rest of the room. So sometimes we write this instead as ETH. I think that's the way that the College Board uses. That's what your book uses, which is why I'm going to take it, okay? Sometimes I've just written it as H or as T, but I think that your book at least uses E sub TH, okay? And thermal energy is equal to the force of friction times the distance, okay? We can remind ourselves that the force of friction is also mu Fn times d, right? So we can kind of use these pieces to put this all together. I had this lab apparatus. I kind of wish I had it. You know what? Next year for AP2, I will have this. So I had this tube that was full of little tiny BBs, little metal BBs, okay? Like a mailing tube. And we did this lab, and it was like the loudest lab that we did ever. So it was like this big mailing tube, right? And I had it like this. And what I asked kids to do is I asked them to flip it over. So you're doing work. You with me there? You're lifting this stuff up. And then what happens? It falls, okay? And as it falls, then the earth is doing work on it, right? And then I turn it again, and then it falls. And I did it, and I made them do it like 100 times, right? And so they're like, oh man, I just had to eat it. I'm like, I don't care, keep turning, right? Da-da-da-da. But we measured the temperature before, and we measured the temperature after. And you want to know what? It went up. And we actually did the math we used because we were doing coefficient of thermal blah, blah, blah. And the amount that the temperature went up was almost exactly what we would expect from the amount of work that we put in. So the work that we put in was all then transferred to thermal energy or heat energy because of the friction when those things fell over and over and over. It kind of works. It's kind of cool. Next year we will do it. I'm so excited. All right. It works? Is that what you said? Yes, is that? No, it's not what you said? Oh, I want to know what you said. Now I'm going to come ask after I give you this problem. All right. Let me give you a problem to try out. Just another way to think about all of this. A hockey puck is given an initial speed of 5 meters per second. The coefficient of friction between the puck and the ice is 0.05. Very low coefficient of friction, right? Which makes sense because it's ice. Did anybody notice the low coefficient of friction out there yesterday when you were walking to your car? Yeah. And I hope that you said to yourself, wow, the coefficient of friction between my shoes and the ground is really, really low. And then you need to think about that, right? It's true. Yeah, that ice, that throws things. Absolutely. The question says, how far does the puck slide before coming to rest? Kind of the same as the Altoids box, except it's you got some information. All right, go ahead and do the problem. Sure. All right. So, lovely physicists, get me started with some good physics. What do I do first? Thanks, Ira. What you got?
I found the force of gravity on the puck, or the force of the earth.
The force of gravity, the force of the earth on the puck. Okay. Oh, how do you do that?
So you know your acceleration due to gravity
Mm-hmm.
is 9.8 or -10.
Okay.
And then you know your mass, or you don't know your mass. So I just
Okay. So you've got that. Cool. All right. What else you got? What's the first thing you wrote down, Brady?
Normal force has to be zero
How do you know that?
because the puck is not going up and down.
Okay. So we can say the force of the earth and the normal force have to add up to 0, F net. In the y direction is equal to 0, which means that Fn equals Fg.
Yeah.
Okay. Cool. That's 2 things. What else do you know? Go, Chris.
The energy of the system at the beginning used to be equal to
Energy total at the beginning equals the energy total at the end. All right. Now I know 3 things. What else I got? Sharing the fun. I want to share. I want somebody else to share with me. Sorry, not that you aren't completely capable. Help me out though. Yeah, go for it.
Okay, so then I went to the energy initial plus the initial force of energy is equal to the kinetic final plus the final.
Like that? Awesome. All right. We're making progress. 1, 2, 3, 4 things. What's the next thing? Go for it, Shishma.
Using cancel out the final kinetic energy because it's asking at rest.
Okay. Didn't you tell me something already? Yeah. I want to share the fun. There's so many smart people in here. I'm not saying, yeah, like all y'all can do this. What's the next thing?
Well, you can plug in velocity into 1/2 mv squared.
Okay, and where does the 1/2 mv squared go? Okay. So 1/2 mvi squared. Okay. Okay. So I'm just going to put that as 5. Okay. What else do I know? I haven't heard anything from this group over here yet. Yeah.
Oh, you can plug in mu times S times V for the initial energy
Oh wait, say that one more time.
You can plug in mu times normal times D
For what?
initial
For this one here? Okay. Okay, so I've got 1 or plus, so mu Fn times D initial, and then do the same thing for the final. Is that what you said? Okay. Fn times D final. Okay. All right, we're making progress, guys. What next?
You can cancel out the thermal initial because distance is
Yeah. So that one goes away. All right. Things are getting exciting. Now what? Yeah. Oh, wait, you've already told me something. Want to share the fun? Go.
Plug in 0.05 for coefficient of friction.
Okay, so we can plug in 0.05 for the coefficient of friction. Sure. Okay, so let me write that down. So that's going to be 1/2 mvi squared. You guys are cute. Is equal to mu mg df. I'm just avoiding putting numbers in for just a second here. But so that one goes in there, and this one goes in here. Okay. All right, we're making progress. We're almost there. Go. The masses cancel out. Oh my gosh, we don't need mass, do we? Catch you later. Bye, mass. Okay. All right. Are we so close? Who hasn't talked to me yet? Go, Josh.
The velocity is 5 meters per second, so we know the left side of the equation is 12.5.
Okay.
Well, Josh, you skipped a step. How did you go from 5 to 12.5?
You square 5 divided by 2.
Okay. So 12.5 is equal to what? 0.05 times 9.8 times how far does that? Oh, wait, no. What am I looking for? How far does it go? Right? Okay, good. So then can I find it? Yeah? Holy cow, DF? Who have I not talked to? What's the answer? 25.5 what? Awesome. Good teamwork, you guys. Nice work. Okay, so here's the thing. What are you going to work on for tonight? The green, all the green, right? All the green papers. There are 2 more here. You have 2 there. You got 4 of them to make sure you got done so we can move it on tomorrow, okay? Thank you guys for your hard work today.